Guys, hope you are doing well. In this session, I will be talking about the second section of chapter 6, which is about the shifting equilibrium. In the previous session, we talked about the equilibrium, we defined the equilibrium position, and then we talked about the equilibrium constant as well. For today, we will be talking about those stresses that disturb the equilibrium position and changes or shifts the equilibrium toward the product or toward the reactant. We have got, guys, 4 stresses. What do we mean by stress? We mean the factors that influence the equilibrium and disturb the equilibrium. Changing some of the conditions in a system, in a reaction, changes the equilibrium or disturbs the equilibrium, shifts the equilibrium toward the product or reactant. We'll be talking about those factors, those conditions today. The factors are what, guys? Are the 4 factors. Here we have got pressure, volume, concentration, and temperature. So today we will be talking about how each of these, changing each of these factors, influence on the equilibrium and changes the equilibrium position as well. In our curriculum, the shift in equilibrium, we mainly depend on theory which we call as the Le-Chatelier's principle, a principle which we call as the Le-Chatelier's principle. So first of all, let us talk about what the principle is all about, and then we will be talking about individual stresses and the effects of those stresses on shifting the equilibrium. The principle stated that if a system at equilibrium is subjected to a stress, so reactant is at equilibrium with the product. We mean the rate of the forward is almost or equal to the rate of the reverse. That's the equilibrium. So subjected to a stress. The stress is what? 4 stresses we have: pressure, temperature, volume, and the concentration of the reactant and product. If a stress changes, one of these changes, what will happen? The equilibrium is shifted in the direction. So changing any of these 4 stresses shifts the equilibrium, or we can say disturbs the equilibrium. The condition, the system is at equilibrium, subjected to a stress, a change in these 4. As these 4 changes, that disturbs the equilibrium. But the reaction has tendency to back to a new equilibrium position. How it backs? Tends to relieve the stress. The reaction spontaneously shifts to the side that relieves the stress and has tendency to back to equilibrium again. So this principle is true for all dynamic equilibria, chemical and physical. We will apply the Le-Chatelier's principle on physical status, physical reactions, and the chemical reactions as well. As the change, the stress in these factors, in these conditions happen, at the beginning we have three positions, we can say. First, the system is at equilibrium. Second, the system subjected to a stress, or we have applied a stress on a system, change it, temperature, concentration, volume, or pressure. And the third position is that the equilibrium the system rearrange itself to back to a new equilibrium position. Let us talk about the first one, which is pressure, and we will be talking about volume as well with the pressure. Guys, change in pressure, we have two pressure. The total pressure, which we will be talking about mainly, and a partial pressure, which we will talk about later. First, let us talk about how the total pressure of a system shifts the equilibrium. A change in pressure affects only equilibrium system in which gases are involved. First of all, we have to know that the systems that the reactions that they do not have gases in the reaction, the pressure has no effect on the equilibrium. We have to consider that the gases in any system, change in pressure of the system changes or shifts the equilibrium position. For example, in this reaction, guys, what do we have? HCl aqueous, NaOH aqueous, NaCl, and H2O liquid and aqueous. State other than gas, pressure has no effect. You have to know that changing the pressure on this system does not change or disturb the equilibrium of the reaction. For changes in pressure that we have gases, what to do? We have a condition. The total number of moles of gas on the left side, meaning the reactant, must be different. The keyword, different, from the total mole of the gases on the right side, which is the product. So in order to let the pressure to shift the equilibrium or disturb the equilibrium, there are two conditions. First, there should be gas. Second, the mole of the gases in the reactant and product should be different and should be different from each other. We will be providing the example for moles different and moles the same. Guys, here we have got SO2 plus oxygen reacts to form SO3. So from the equation, 2 moles of SO2 reacts with 1 mole of oxygen. Totally, we have got 3 moles in the reactant and 2 moles in the product. In this case, pressure affects. Why? Because we have gases, the system, the reaction is gaseous reaction, and then the moles of the reactant is differ with the mole of the product. So pressure effect is because number of the moles in both sides are different. How it works the pressure? Of course, we'll be providing the increasing pressure favors or shifts the reaction toward the lower amount of the mole. Decreasing pressure favors the reaction or shifts the reaction toward the higher amount of mole. If we increase pressure on this system, favors the forward direction or shifts the equilibrium toward the forward, but reducing the pressure favors or shifts toward the reactant. If two sides of equation has same number of moles, the change in pressure has no effect on equilibrium state, guys. Example, here 1 mole of H2 reacts with 1 mole of Cl2 to form 2 mole of HCl. 2 moles exist in the reactant with 2 mole of the product. Changing, increasing, decreasing pressure of this reaction of this system does not shift the equilibrium because the moles of the reactant is the same as the moles of the product. Here we have got an example. They have a process for production of ammonia, guys. A Haber process is a method that the ammonia can be formed from the elements of nitrogen and hydrogen. Here 1 mole of nitrogen reacts with 3 moles of hydrogen, which totally 4 moles of gases exist in the reactant, and to form 2 moles of ammonia, so 2 moles of ammonia in the product. In this case, changing the pressure of the system affects or shifts the equilibrium. How it affects? An increase in pressure causes increase in the concentration of all species because volume decreases. And we have studied this in grade 11, guys, PV equal to nRT. As you can see, the pressure and volume, they're inversely proportional to each other. Increase in pressure is the same effect as decrease in volume, and vice versa as well. The system then can reduce the number of molecules and the total pressure by shifting the equilibrium to the right. Why to the right? As I told you guys, increasing pressure always favors or shifts the reaction, the equilibrium toward the lower mole of gas. Lower mole of gas. Decreasing pressure shifts toward the higher mole of gas. Higher mole of gas. Guys, you know that pressure is inversely with the volume. So increasing pressure means decreasing volume. Decreasing pressure means increasing volume. So whenever the pressure increases and volume decreases, the shifting is toward the lower amount of gas, but volume increases and pressure decreases, the shifting is toward the higher amount of gases. So in above, guys, increasing pressure favors the forward or shifts toward forward, right? Because it's toward the lower mole. Reducing pressure favors or shifts the direction toward the reactant, which is toward the higher amount of mole. New equilibrium pressure is still higher than before. It's not as high as pressure caused by the initial stress. Guys, initially when we apply or when we change the pressure, increase the pressure or decrease the pressure, during the disturbance of the equilibrium position, the pressure or the stress is high, but the reaction, the system rearrange itself automatically to back to a new equilibrium position. The new equilibrium position, the pressure is higher than before, but it's not as the initial pressure when we applied. It's not the same as the pressure that we applied at the beginning of a disturbance of equilibrium state. If pressure increase or volume decrease, guys, shift is toward the fewer number of moles. So increasing pressure shifts toward the product side. If pressure decreases or volume increases, shift is toward the greater number of moles. So here in this case, shift is toward pressure reduces or volume increases, shift is toward the reactant side. But guys, changing pressure of the system does not change the equilibrium constant. So you have to know that the equilibrium constant changes only by temperature, does not change by pressure. We have some notes, guys. The addition of the inert gases to the systems, we mean those gases which are not reactive, like the noble gases, guys, the noble gases, helium, neon, argon, krypton, and xenon as well, into the reaction vessel for a system of ammonia or any system increases the total pressure in the vessel. Totally, it increases the total pressure. But it does not change the partial pressure of the reaction gases. So increasing or addition of the inert gases to the system does not shift the equilibrium position. So increasing pressure by adding a gas that's not a reactant or product, these gases are not a part of the above equation, above system, does not shift the equilibrium, cannot affect the equilibrium position of the reaction system. And then there will be something like that, liquefying ammonia. Liquefying ammonia. Liquefying ammonia in the above reaction, we mean taking ammonia gases to be ammonia liquid. So whenever we use the liquefying ammonia in the Haber process, we mean removing the ammonia gases in the system. We'll be talking about concentration, guys, as something removed in order to compensate the removal of that. The shifting goes toward the species that we removed. So liquefying ammonia shifts the forward direction. You have to know that. Shifts to the right during its production. Increase in partial pressure. We said we have two types of pressure. We talked about the effect of the total pressure and when it works. The partial pressure of a gas is same as the concentration gas. And in concentration we'll be talking about this. The increase in partial pressure of a gas is not related to the amount of the gases in the reactant or product. Whenever we increase a partial pressure, that means we increase the concentration of the nitrogen something, or decrease partial pressure, that means we remove. So increase in partial pressure of any species in gaseous state, that favors the direction toward the opposite side. Decreasing the partial pressure of any species in the gaseous state, the gaseous species, decreases the concentration, so favors the shifting toward the species which decreases the partial pressure. We'll be talking about partial pressure and concentration as well. So let us talk about the concentration, guys. The second parameter that we will be talking about in shifting equilibrium is what is concentration. Concentration, an increase in concentration of reactant is a stress on the equilibrium system, or product as well. Increasing or decreasing the system that will shift the equilibrium. So changing the concentration of gaseous substances and aqueous substances as well changes or shifts the equilibrium. But those substances which are solid and liquid, changing their concentration does not affect on the equilibrium. We'll be talking in detail. An increase, guys, suppose we have a reaction here, AB goes to CD. Guys, increasing A shifts the direction toward the product, so increases C and D, but consume B, so the B decreases. Consume B. Equilibrium is reestablished with the higher concentration of A because we increase it, and the addition but a lower concentration of B. Why? Because B consumed here. As a result, concentration of ACD increases, but B decreases. So let me tell you guys, in concentration, first you have to check whether it's gas, aqueous, solid, or liquid. If gas and aqueous, changing the concentration affects, I'll be talking about that, how it affects. But solid and liquid, changing the concentration does not affect on the shift in equilibrium. How the gases and aqueous affect is increasing the gaseous amounts or aqueous amounts in any side favors toward the opposite side. Decreasing any of those favors the direction or shift the direction toward the species that we decrease it. So let me tell you, increasing A favors toward the product. Why? Because we increase it in the reactant. The opposite side is the product. As we increase A, phase shifts toward the product, so must consume B, B reduces, and AD increases. Let me increase B. Increasing B still favors the forward direction because we increase it as pressures in the reactant. Increasing B consume A, so A reduce, C and D increase. Another case, let us increase the product. C increases. Increasing C favors the direction or shifts the equilibrium toward the reactant, reduces D but increases B and A together. Let us reduce D, reducing D. We said when we remove something, the direction shifts toward that. So when the direction shifts toward, the C increases. Why? Because there will be production of more C, and B and A decreases, both consume. If we reduce something in the reactant, A reduces, the shifting goes toward the reactant side, reduces C and D consumed, and B increases as well. So that's how the concentration works for the shifting the equilibriums, guys. And increasing the concentration of CD shifts the equilibrium to the left. Why? Because increasing C or D, it shifts to the reactant. They are existing in the product. So we talked about this, the cases that decrease in D, what will happen? Decrease in D favors toward the product, increases C, and decreases the concentration of AB, consume A and B. Changes in concentration have no effect on the value of equilibrium constant. So equilibrium constant does not change by changing the concentration of the reactant and the product as well. Here we have some notes. The concentration of pure solids and liquids do not change. So when we write the equilibrium expression, only gases and aqueous are written. As the concentration of solid and liquid are not changing, the equilibrium, they will not appear in the equilibrium expression. For example, here we have gas and solid. We do not include the solid. Instead of that, we'll write down 1 over concentration of ammonia, which is gases, HCl, which is gas. Again, for the ionization of HF, where HF is aqueous, reacts with H2O, which is liquid, to form hydronium and F aqueous. The aqueousness of hydronium and F includes to the equation, but the liquid H2O does not include. So when we write the equilibrium expression for this equation, we have to not include the water into the equation. The same, the reaction of Kw, when we write the Kw, we multiply the hydronium by the hydroxide. We do not include the H2O in the constant ionization of water as well. Adding catalyst, we may guess that adding catalyst speed up the rate of the reaction and it affects on the equilibrium system. It's not the case. Adding catalyst has no effect on equilibrium state. So guys, adding catalyst to a system does not shift the equilibrium toward any side. Instead, just it affects on the rate of the reaction. If any concentration of reactant, so reactant increases, or product decreases. Always, in this case, reactant increase, product decrease, shifts toward the forward. Or concentration of the reactant decrease, product increase, favors the direction toward the reactant or the reverse favorite. Increasing partial pressure means increasing concentration. We said As increasing partial pressure of a species means we increase the concentration. Increasing concentration favors toward the opposite side. Decreasing the partial pressure, decreasing concentration favors toward the side which the gas removed. Let us answer this question, guys. Here we have a gaseous system. A gaseous system, we mean all the reactants and product are gases. If we increase or partial pressure of the product increases, product means NO2. Partial pressure of NO2 increases means its concentration increases. Concentration of product increases always favors the reverse direction. Shift is toward the reverse. That's how the concentration works. Let us talk about the third factor which changes or shifts the equilibrium regardless to the physical status. So temperature, whenever talks about temperature, always it works. Whenever the system is gaseous, solid, liquid system, there should not be any restriction for the temperature. The reactions, guys, reversible reactions are exothermic in one direction and endothermic in the other direction. So here we cannot say always increasing temperature favors toward a side, decreasing favors toward the another side. We have to know that the reaction is its endo increasing will favor to a side, decreasing temperature will favor to another side. Exo, just the opposite, favors toward different sides. For example, guys, a formation of the ammonia is an exothermic process, releases 92 kilojoules. And the decomposition of ammonia is endothermic process. If temperature increases, guys, if temperature increases, always equilibrium state shifts to the absence of heat, endothermic side in an equation. To increase in temperature, always the shifting goes toward what? The endothermic side. But decreasing temperature always shifts toward the presence of heat side, which is the exothermic in the equation. What do we mean by this, guys? Let us apply on the above equation. Or this is the equation which is given. Here this equation is what is exothermic. Exothermic. High temperature favors the decomposition of ammonia, the endothermic reaction. When we increase the temperature, we said increasing temperature shifts the reaction toward the endothermic side. In this, the forward is exo, but the reverse is endo. So increasing temperature favors the endothermic side, which is what the reactant, formation of the reactant will be favored. How about decreasing temperature favors toward the exothermic side, which is the product, formation of the product. So when temperature increases, reactions shift to left side. Why shift to left side? Because the left side is endothermic. The favorite direction toward the left side. The reverse is endothermic. The forward is exothermic. Or guys, I have provided a note here in order to know how the temperature works. If the sign of the enthalpy and the sign of temperature are both the same, we mean what? For example, endothermic reaction, which is delta H, is positive for endo, and increasing temperature, which temperature increase can be, increasing temperature can be represented by positive. This. Or for exothermic, delta H is negative, and decreasing temperature is negative as well. Decreasing represents by a negative sign. So if the sign of the temperature and enthalpy are equal, always the shift is forward direction. In these two cases, always the favorite direction, or the shift in equilibrium goes to the forward. But guys, if enthalpy is positive and temperature reduces, what will happen? Reducing temperature, T is negative, the opposite sign, or delta H is negative and T is positive. In these two cases, always favors the reverse direction. This is a simple tip, a simple technique in order to know how the temperature works, guys. Have a look on this Haber process. When we have a Haber process, we mean formation of ammonia. Let us do it by the technique we said. It's exothermic, so delta H is negative. Increase in temperature, guys, increase in temperature, T is positive. Favors what? The reverse direction. Decrease in temperature, which is negative, favors the forward direction. When temperature decreases, equilibrium shift to the right. Why? Because I told you that the signs are equal, the shift is toward the forward direction. At low temperature, the forward reaction is too slow for the Haber process to be commercially useful. Moderate temperature of 500 Celsius, this is the temperature of the Haber process. I prefer to you to know the conditions of Haber process. And a very high pressure, almost 700 to 1000 atmospheric pressure, produces satisfactory yield of ammonia. So in this temperature and this pressure, the formation of ammonia will be in a industrial scale, and then will be high enough in order to be industrially produced. Have a look on this example which is given in our book, guys. Said when we have nitrogen dioxide goes to dinitrogen tetraoxide, the color of nitrogen dioxide is brown. It's written, which is what? Brown. And the color of dinitrogen tetraoxide is what? Is colorless. Colorless. Okay. Let us test how increasing temperature in this direction 0, 2500 lets the container to be more Brownian. Guys. This reaction releases energy. It's what? Exothermic. So the enthalpy of the reaction is negative. Increasing temperature is positive. Increasing temperature means positive. These two are opposite, so there should be the reverse, shifts the reaction toward the reverse direction. As it shifts toward the reverse, what will be formed more? The nitrogen dioxide. What's the color of nitrogen dioxide? Is Brownian, and that's why increasing temperature increase the Brownian color in the container. Decreasing temperature, the brown becomes fainter and becomes colorless as we decrease much more pressure. Why? Because when we decrease temperature has the same sign of the enthalpy. So at that time we'll favor the forward direction, and then we'll let the nitrogen dioxide to be consumed, the brown nitrogen dioxide, to form a colorless dinitrogen tetraoxide. That's a simple example which represents how the temperature changes the color of the systems and shifts the equilibrium toward the systems. Let us take some notes, guys. The change in temperature changes the K. How it changes the K? When temperature favors forward, so can be increasing, in some cases can be increasing temperature or decreasing temperature. But whenever the temperature, increasing temperature, favors the forward direction, in that case K will be increasing. But if temperature decreasing or increasing temperature favors the reverse, that reduces the value of K. That's how it works. Whatever the types of temperature change, increasing or decreasing, as I told you guys, kind of thermal equation, endothermic or exothermic, K value increases on shift forward and decreases on shift in reverse. So you have to know that how temperature changes K. When it shifts forward, it increases the K due to of temperature only. When it shifts reverse, it reduces the value of K. Change in pressure, again, concentration and adding catalyst has no effect on the K. Do not forget this. Adding catalyst has no effect on the K equilibrium state. Why? Because catalyst increase the rate of the forward and the reverse equally, and that does not change the equilibrium constant of the system. Physical state is not considered when temperature changes. I told you whenever we talk about temperature, we do not include or consider the physical limitation. Or does not shift the equilibrium system. Adding NH4Cl. NH4Cl, it's solid, and concentration of NH4Cl, the solid is and liquid is, does not change. That's why it does not affect, because it's solid. Increasing pressure. You set the pressure of the system. Increasing pressure works. Why? Because we have different moles of gases from reactant to product. In the reactant 2, in the product 0. Increasing pressure favors to have the lower mole of gases. So the forward is direction is favored, and K does not change because it's the increasing pressure. Increasing volume is the same as decreasing pressure. Decreasing pressure favors the formation of the higher mole of gas, which is the increasing volume. Decreasing pressure favors the production of the higher mole, which is the forward. This should be forward. Reverse. Reverse direction is favored. Why? Because it goes from 0 to 2, which is a higher mole. Adding catalyst does not affect the equilibrium system. It does not change the position of the equilibrium. Increasing temperature, T positive. These two are opposite, so reverse must be favored. The reverse favorite. And guys, whenever due to temperature reverse favorite, that decrease the value of K. Value of K decreases. Decreasing temperature is negative. Negative with negative, the forward favorite. When forward favorite, the value of K increases. Adding CO2 gases. Do we have CO2 in the above equation, guys? We do not have. It's just the same as addition of krypton. So it does not affect because it's not in the reactant and product of the system. Whenever we do not have a species in the system, addition or removal of that species does not shift the equilibrium position. We have so many other, which one shift the equilibrium to the right side? Let us, the first, second, and third, decreasing the volume of container. Here we have a gaseous system, 3 moles of gas in the reactant for 3 moles of gas in the product. 1 plus 2, 3 moles in the product. Decreasing the volume of container. Guys, whenever the mole of gas is in reactant and product equals, the pressure and volume, changing pressure and volume does not affect on shifting. Increasing the temperature. Get set delta H is higher than 0. That means delta H is positive. Positive delta H, and increasing temperature, that means T positive. This shift is the forward direction. So in this case, forward favored and K increases. Using catalyst does not shift, so only which one shifts to the right, which is forward? Only B is correct answer, which shifts toward the right side. In this section, we have some reactions that goes to completion. We'll be talking about those reactions that goes to completion due to of specific effects, guys. We have got 3 reactions that goes to completion because of different reasons. Let us talk about each of them in detail. Some reactions involving compounds formed by chemical interaction of ions in solution appear to go to completion in the sense that the ions are almost completely removed from the solution by what? By the formation of a gas, formation of a precipitate, and formation of a slightly ionized molecule in the product. Let us provide an example for the formation of gas, how it works, guys. The formation of gas, of course, the gas must be formed in the product, Have a look when carbonic acid decomposes will form H2O and CO2. Here the CO2 is gases and it escapes from the system. Guys, logically, if a product formed and this product continuously removed from the system, so it must be in an open system, the system, in order to go to completion, otherwise it will not go to the completion, there will be a reversible reaction. If the CO2 continuously removed from the system, what will happen to the reaction? There will not be enough CO2 to combine with H2O and back to form carbonic acid. In this case, the reaction tends to completion. It goes to completion. This reaction goes partially to completion because one of the product, which is CO2, escapes as gas if container is open to air. If closed container, there is equilibrium, guys. So in order for formation of gas to go to completion, the system must be what? Must be an open system in order to let the product to go to completion. And the reactant must not be the gaseous reactant. Why? Because whenever we have gases in reactant, when there is gases in reactant, that means the system is closed. You have to know that the gases in reactant means the system is closed. Let me provide an example to that, guys. H2 plus I2 will produce 2HI. Gas. You may guess here in this case there is a formation of gas in the product. This is not a reaction that goes to completion. Why? Because whenever we have gases in reactant, it represents the system is closed. It represents the system is closed. And whenever the system is closed, that gaseous product is not able to escape, and then there will be a reversible process. When a strong acid is added to an aqueous solution of baking soda or sodium bicarbonate, we can say, carbon dioxide is formed, guys. In this equation, the net equation shows that ions are removed. The spectator. Hydronium plus bicarbonate reacts to form H2O and CO2. So CO2 is, if the system is open, that leads to completion because of escaping the gases in the system. How do we know the system is open? Because here we do not have gases in the reactant. That tells us the system is open. And then this arrow is representation for what? For escaping the gas in the system, or gaseous phase escaping in the system. Formation of a precipitation, guys. Whenever some species, a salt or any other, formed in the product as precipitate or precipitates, a precipitate is not able to dissociate and form ions and back to form the reactants. So those reaction goes to completion and completed. NaCl reacts with AgNO3 to form AgCl, which is a precipitate, plus sodium nitrate. Here in this case, guys, in order for reverse direction to process, there should be the ions of AgCl and NaNO3. But because AgCl is a precipitate settled out in the container, at the bottom of the container, that's why the AgCl are not able to combine with NaNO3 to form the reactant side. In this case, the reaction goes to completion. Why? Because completely these two are forming the product, and product is not able to back to form the reactant. That reaction goes to completion. So the formation of precipitate is one of the factors that leads the reaction to go to completion. Color of the precipitate silver chloride here is white. This is just as a note to know what's the color of AgCl. It's a white precipitate. The third reaction that goes to completion, which is the formation of a slightly ionized molecule. Guys, you may remember that neutralization reactions of which was the reaction of hydronium and hydroxide formed H2O. H2O in the reactions is a slightly ionized molecule. Is a slightly ionized molecule. If a slightly ionized molecule formed, this slightly ionized molecule has little tendency to back to form the reactant. So the favorite direction in this case is toward the formation of the slightly ionized molecule. The slightly ionized molecule has no tendency to back to form the ions. That's why the procedure, this reaction, we can say that it goes to completion because of formation of H2O in the product, which is a slightly ionized molecule. When clear sodium chloride solution is combined with a clear silver nitrate, an insoluble white precipitate of silver chloride is formed. Here we have got the precipitate of AgCl, which is a white color, and then when the precipitate of AgCl formed at the bottom of the container, the reaction goes to completion. It has no tendency to be a reversible reaction. The last part in this section is about the common ion effect. Common ion effect we'll be talking about can be formed from the combination of two ions in common but from different sources. Two ions in common, two ions, the same two ions which are common to each other from different sources. Usually one from the acids and bases, the other from the salts. Addition of an ion, guys, addition of an ion common in two solutes. So from two solutes, usually one of them is salt plus the other which is acid or base. Two solutes. They have an ion which are the same and common to each other. Bring us what? A precipitation or reduced ionization is an example of common ion effect. So whenever we add the solution of two solutes, one salt usually, the other acid or base. This leads to two conditions, two things will happen. First, the formation of a precipitate. Second, the decreasing the ionization. The formation of a precipitate is for the strong acid and base, but reducing ionization is for the weak acid base. So reduces ionization when the common ion is between a salt with the weaks, increases the precipitation when the common ion is between a strong with the salts. Adding common ion has two effects: increased precipitation of saturated solution for strong acids and bases, decreases ionization of weak acid or weak bases. So the ionization refers to the weaks, the precipitation refers to the strongest. Let us talk about the first, increasing the precipitation of a saturated solution for strong acids and bases. Have a look on this example. HCl, which is a strong acid, form hydronium and Cl negative. In this case, just provide an example of a salt that contains Cl. For example, NaCl. NaCl dissociate to form Na and Cl. Guys. When we add these two together, what will happen? Let me tell you what will happen. You know, guys, this Cl from the NaCl is common with the Cl from HCl. This is the common ion. And whenever the acid, as I told you, one of the solute must be salt, the other acids or bases. Whenever the acid or base is strong, That means the precipitation of the salt will be formed. How? Logically, guys, when these two combines, what will happen to the shifting? What will happen to the shifting? In this direction is not favorite to form the HCl. Why? Because this is strong acid. Strong acid, as even if it form, it will completely ionize to form back, to form the ions. So the favorite direction here is the forward direction. That's why the shifting equilibrium does not shift us in the first equation, in the acid equation, or the strong acid or the strong base equation. Instead, the Cl backs Gl and increases this Cl in the second equation, the equation of the salt. And when it increases the Cl in this equation, the extra amount of Cl reacts with Na to form the salt. Of course, in a saturated solution. The solution must be saturated in order to form the insoluble NaCl. Otherwise, if it's not saturated, NaCl will dissolve. So in this case, guys, whenever it's strong acid or strong base, the favorite the shifting direction will be in the reaction of the salt, and how it goes, the ions, the common ion combine and shift is to react to form the salt in a saturated solution. This will be a precipitate. What will happen to the other ion, the cation? Reduce, of course, because when we increase Cl, that consume the Na, in total we can say the concentration of Na reduces and the precipitation of NaCl increases. Adding common ion like Cl into a saturated solution increase precipitation because it shifts to the left. It shifts to the left, guys. It shifts to the left. As you can see that adding this to Cl increases the Cl and reacts with Na, shifts to the formation of the salt, and the salt in a saturated solution precipitated. This is true for the strong bases as well, guys. So whenever we add in general strong acid, what will happen to the salt of that strong acid? A strong acid with a salt that has a common ion with that acid. HCl, NaCl, H2SO4, MgSO4, KOH, KCl. Okay, here in this case the positive becomes the common ion, sulfate is the common ion. That's how we can provide examples. What will happen? Increase the concentration of the common ion in the solution, and this disturbs the equilibrium system. In which direction? According to Le Chatelier's principle, some of the added Cl combine with an equivalent amount of Na ion and some solid NaCl precipitate out. So the addition of the Cl combines with Na to form NaCl. New equilibrium has a greater concentration of Cl, but a decreased concentration of Na. As I told you, any consumer. Shift toward the reactant side in the salt equation. So adding common ion increases precipitation of a saturation salt. K value is the same. So this addition of the common ion does not change or affect on the value of equilibrium constant. This was about the strongness. How about the weaks? Addition of a common ion of a salt to a weak acid or weak base, what will happen? Instead of talking about precipitation, we will be talking about ionization. So in this case, reduces ionization. Let us provide examples how. Decreasing ionization of weak acids or weak bases. The common ion effect is also observed when one ion species of a weak electrolyte, we mean weak acid and weak bases, added to an excess solution, to a solution that has the common ion of that weak. What will happen when we add sodium acetate into acetic acid solution, guys? Have a look on both equations, guys. This is acetic acid ionized to form hydronium and acetate. Sodium acetate will produce sodium ion and acetate. As you can see, notice that the common ion here is acetate. Acetate is the common ion in between these two solutions, these two solutes. Guys, as you can see, the reaction of the acid is a weak acid. It's a reversible reaction. So any shift, any addition of these two will increase, can shift toward the reactant side in the reaction of the acid. Because it's weak acid, a reverse is much favorite in this equation. So addition of acetate from sodium acetate to the acetate, these are the common ions, will increase acetate ion. As it increases acetate ion, the increase in any species, which is aqueous or gaseous, in any side favors toward the opposite side. So in this case, favors the reverse direction. As it favors the reverse direction, what will be consumed? Hydronium. So the concentration of hydronium in this case reduces. What will be formed? Concentration of the weak acid increases. What's the direction? Reverse favorite. And what will be the ionization? This acid ionizes in the forward, but in this case reverse is favorite. So ionization of the weak acid reduces. That's how we said decrease in ionization of weak acids or weak bases, because it favors or shifts the equilibrium toward the reactant side, the weak acids and weak bases for the weaks, guys. Let us talk about the pH, pOH, hydronium and hydroxide, guys. When, keep in mind, weak acid added to a salt that has a common ion with the weak acid, common ion with the weak acid. Okay? The following will happen. Reverse favorite, as reverse favorite, the concentration of the weak acid increases, the concentration of hydronium decreases. As concentration of hydronium decreases, also we can say ionization of the weak acid, ionization of weak acid reduces. Non-ionized molecule is the same as the concentration of weak acid increases. Hydronium reduced. What will happen to pH? pH increase. What will happen to the hydroxide? Hydroxide increase. What will happen to pOH? pOH decrease. So the equilibrium shifts in the direction that uses some of the added acetate ion in the according to the Le Chatelier's principle. More molecules of acetic acid are formed. This is the concentration of acetic acid. The concentration of hydronium reduces, and when concentration of hydronium reduces, pH of the solution increases. The addition of a salt with an ion in common with the weak electrolyte reduces the ionization of the electrolyte as well. Reduces the ionization of the weak electrolyte as well. You can see these are two solutions. We added them together. The solution of what and what? Here it's written acetic acid with sodium acetate, which we talked about. These two, when we add it reduces hydronium and increases the pH. The pH reaches to 4.48, which is a high pH than to be the pH of acetic acid. Both contain the common ion of acetate, guys. They produce a solution on the right, which is only slightly acidic due to the decreased ionization of the acid. The colors of the solution are due to addition of an acid-base indicator. These two colors, the green and the red, due to we have added indicator to those solutions. That's how when we add them together, they have a common ion in between, which is acetate, and reduce the hydronium of the solution, or we can say increase the pH of the solution. When we add a weak base with the salt, which they have a common ion in between, like ammonia plus ammonium chloride. Okay, these two, they are in common with each other. What will happen, guys? When we have the weak base is the reversible direction. So the favorable direction is toward the reactant. The weak base will produce ammonium, and then ammonium chloride will produce ammonium as well. These two are common ions from two solutions. Addition of ammonium to the above ammonium increases the ammonium in the above solution, and then increasing this reacts with hydroxide, decrease the hydroxide, and shifts the equilibrium toward the reactant side. In this case, guys, when it reverse favorite, what will happen to the concentration of ammonia? Increase, of course. What will happen to the concentration of hydroxide? Decrease. Why? Because there will be consumption of hydrogen hydroxide, NH4 positive concentration increases, and then what will happen to the ionization of ammonia? Ammonia ionizes in the forward direction, but if it's reverse favorite, so the ionization of the ammonia reduces. As the hydroxide reduces, that increases the hydronium. As the hydroxide reduces, the hydronium increases, that pH reduces as well, and POH increase. So keep in mind, guys, let me write the summary to you in this part. When a weak acid plus the salt which they have common, when a weak base plus a salt which they have common in. Example, in order to know that, a weak acid, for example, HF plus KF. Here NH3 plus NH4Br. Okay? Addition of a weak acid to a salt, which are the common with each other, always reverse favorite. Here also reverse favorite. Concentration of the weak acid increase, concentration of the weak base increase. Bash. Okay. And then when the concentrations increases in the solution of the weak acid, reduces always hydronium, and when it reduces hydronium, it will reduce the POH as well, but increase the pH and hydroxide concentration. But for the weak base, it reduces the hydroxide concentration. When it reduces the hydroxide, that means reducing the pH of the solution, and then hydronium increases, and then POH decreases as well. POH increases as well. So in general, we can say a common ion of the weak acids, weak bases with their salts that they have ion common, reduces for the acid hydronium, for the base hydroxide. Here increases the pH, and hydroxide. Here increases the pOH and hydronium. In general, we can say the value of hydronium and hydroxide reducing, but the pH and pOH are increasing. What? Here hydronium reduces, but the pH increases. Here hydroxide reduces, but the pOH increases. That's how we can answer the types of the questions in this part. Let us solve some ministerial exam questions, guys, in this section. When pressure increases to this system, what will happen? We have a gaseous system, 2 plus 1, 3, goes to 2 moles of CO2. Increasing pressure favors the formation of the weaker, so what will be formed? CO2. Amount of CO increase? No. CO2 decrease? No. Amount of CO2 increase? C is the correct answer, because forward is favored. Reaction tends to completion if products have high melting point. No, we didn't talk about that. Are liquid? Are precipitate? Yes, because if the products are precipitate, reaction goes to completion. Effect of common ion causes increasing what? Increase common ion, decrease ionization, but increase what? Precipitation. When precipitation increases, that means reduces solubility. So that we can say increase precipitation, but solubility reduces. If it says reduce what? We can say reduce solubility, or we can say reduce ionization as well. But in this case, increases what? Precipitation of the salt in a saturated solution. The value of equilibrium constant in endothermic reaction is by increasing temperature. So whenever delta H is positive endothermic and temperature increases positive, these two positive, what will happen to the direction? Forward favorite. And as forward favorite, what will happen to the K? Increases. Higher equilibrium constant expresses that higher value of K. Concentration of product greater than the reactant? Yes. Concentration of reactant greater than product? No. Concentration of product and reactant are equal? No. Does not depend on temperature. So this is the concentration of product greater than reactant with equilibrium reached. Question 6 to 8, let us solve according to this equation. Decrease in temperature, so let us take the sign of the temperature. Delta H is negative, decrease in temperature is negative, negative forward favorite, and increase the value of K. Shift to the right and decrease K? No. Shift to the right and K increases? Yes. This is the B is the correct answer. Increasing pressure. Here we have got 4 moles, there 2 moles. Increasing pressure favors the forward direction. Equilibrium shift product side and K increase? No. K does not change. K does not change. Equilibrium shift product side and K does not change. C is the correct answer. Removing some N2 gas. Removing N2 gas favors the reverse direction. Shift to the right and no. Shift to the right, no. Shift to the left. Shift to the left, K does not change. C is the correct answer. Why? Because the shifting due to of the concentration does not affect on the K. Another question, which of the following factor below will favor high concentration of the underlying substance? Underlying substance is in the product. So any of these favors the forward direction, shift as the forward direction will be considered as the factor that increases the CO2. Increasing reactant concentration, the concentration of reactant, yes, forward is favored. Increasing pressure of the system. Let us check. We have two moles here, one mole there. Increasing pressure favors reverse, so it's incorrect. Decreasing temperature, this reaction is endothermic, positive, and T decreases, negative. These two are opposite, so favors the reverse direction. And addition of the catalyst, so A is the correct answer, which is increasing reactant concentration, which is the PCl5. The endothermic reaction, which is positive, in equilibrium state, when temperature decreases, it increases what? Temperature decrease means negative. These are two opposite signs, so reverse favor. As reverse favor, concentration of product increases? No, decreases. It increases what? Equilibrium constant value? No, it does not increase the equilibrium constant value because it's reverse. It increases the concentration of reactant. Yes, it increases the concentration of reactant because here we have got reactant there product. There will be more formation of reactants. Both A and B, no, it's not correct. This reaction, again, it's given by liquefying ammonia. Guys, liquefying ammonia means removal of ammonia, so shift is the forward direction. Partial pressure of ammonia gas increases, no. K value increases, no. Forward reaction is favored, yes. A chemical reaction is in equilibrium when forward and reverse reaction rates are equal. C is correct answer. If the equilibrium system, the temperature increases, so the value of K. This delta H is positive, T positive, so K value increases, of course, because the forward is favored due to temperature. After adding potassium cyanide to solution of cyanic acid, the pH value of solution, guys. This is weak acid plus the salt which they have a common. In this case, reverse favorite hydronium for the acid reduces and the pH of the solution increases. Chemical equilibrium's constant value depend on change in temperature, pressure, concentration, all of them. The equilibrium constant depends on temperature only, guys, you have to know. For the equilibrium system, when pressure decreases, here we have got 2 moles of gases, there are 2 moles of gases. The quantity of NO increases, no. When pressure decreases, in this system increasing or decreasing pressure has no effect. The quantity, no. The quantity in the system does not change. B is the correct answer. In this solution, in this reaction, we have a Brownian NO2 and a colorless N2O4. The temperature is rising to 100. How will the color of the container changes and the amount of N2O4 change? Guys, the above reaction, delta temperature increases, that means positive, and then the enthalpy is negative, so the reverse is favorite. Reverse favorite, that means the N2O4 reduces and color becomes Brownian. It becomes Brownian and N2O4 is high. It becomes Brownian and N2O4 is low, reduces. If exothermic reaction reach to equilibrium, so by increasing temperature, exothermic means negative, increasing temperature means positive, forward or reverse favorite, reverse reaction is favorite. The common ionosphere causes to increase, this is second time appears in ministerial exam, the precipitation increases the precipitation. For this exothermic reaction, so means the delta H is negative. The direction of the reverse reaction is more favorite as, okay. Favorite reaction will be reverse when pressure decreases. Let us check. Here we have got one gas, there are 2 gases. Pressure decreases it will be forward. Why? Because from the lower goes to the higher. Temperature increases, T is equal to negative. This will be reverse. So then said reverse, so B is the correct answer. Reactant concentration increases. Reactant concentration increases. One of the reactant, for example, hydrogen increases. That will be forward direction. And both A and B are correct. Both A and B is not. Pressure decreases. As the pressure decreases, the amount, the direction goes from the lower to the higher mode. But as it increases from the higher toward the lower mode. So temperature increase is the correct answer. Guys, do not include the carbon because carbon is solid for the pressure. When sodium acetate is added to an acetic acid solution, sodium acetate, weak acid, with a salt of that weak acid, what will happen? Hydronium concentration increase? No, in this case hydronium reduces. As hydronium reduces, CS3COO precipitates? No, because in weak acids and weak bases there will not be a precipitation of the salt. The ionization of the weak acid decreases. Yes, of course, the ionization of the weak acid decreases. Guys, for the shift in equilibrium, let us solve the critical thinking in the section review of section 2. The critical thinking stated that carbon dioxide and water react to form bicarbonate. So the carbon dioxide with water reacts to form bicarbonate and hydronium ion in the medium. Hyperventilation, which is a process of rapid breathing. Whenever we rapid breathe, we call as the hyperventilation, causes more carbon dioxide to be exhaled than normal. Causes more carbon dioxide to be exhaled than normal. So when we breathe rapidly, we exhale more carbon dioxide to the surrounding, from our body to the surrounding. How will hyperventilation affect the pH of blood? So it's asking what will happen to the pH of the blood while during the hyperventilation, guys. The procedure is that when it says during hyperventilation carbon dioxide removed from the body, that means in the equation we remove the CO2 from the system. As CO2 removed, CO2 is gas, so that lets the shifting go toward, or the reaction shift toward the reactant side. What will happen when the reaction shifts toward the reactant? Of course, the hydronium and bicarbonate must react to form the H2O and compensate CO2 as well. The removal of CO2, the amount which removed. So in this case, what will happen to the hydronium concentration? The hydronium should be consumed to form the reactants. So its concentration of hydronium reduces. So the hyperventilation lets the hydronium concentration to be reduced in our body. As the hydronium reduces, what will happen to pH? pH increases. That's the answer. Hyperventilation increases the pH in our body through reducing the hydronium. Thank you for the attention, guys.